This is group 58, recitation 10 discussion.
All right, so for this week's recitation, it says that they want to give us some experience using the energy principle applied to real multi-particle system and the corresponding point particle system to make predictions about the system's behavior. The first problem is about a bicycle wheel. It has a rim of mass big M and an axle of mass little m. The masses of the wheel's 10 spokes are so small that we can neglect them, which is always nice. So starting off, initially the wheel is resting on a horizontal surface. You hold the axle on each side so that it doesn't tip over. And at t equals 0, you exert a horizontal force of magnitude F on the axle so that the wheel begins to roll without slipping. So the first part asks, what is the wheel's speed when you pushed it forward a distance d? So we know that the kinetic energy, the translational kinetic energy plus the rotational plus vibrational, but there's not any in this case, is equal to the total work. And so we know K trans can be represented as 1/2 mv squared, but because we have the two masses, we need the total mass. And then the rotational is the same, but in this case, the mass of the rim is only taken into consideration because the axle isn't spinning. We kind of just neglect it because it's not like, it doesn't have a large enough radius to make a difference. Then we set it equal to force times distance. And then if you work out the math, you find that the velocity is equal to root FD over big M plus 1/2 little m. Did you guys get that?
Yeah,
Yeah.
same thing.
Okay. And then part 2, it says determine the magnitude of friction force that the surface on which the wheel rolls exerts on the wheel while you are pushing it. So this is the translational component from the part 1. You see it looks exactly the same. And so we set that equal to the force applied by your hand minus the force of friction over distance. And so we know that the velocity after it's pushed at distance d is equal to FD over m plus 1/2 little m, because we also solved that in the last problem. So you substitute that in for v squared. You can see it's the same, it's just the square roots removed. And it's a lot of algebra to get it to this point, but I saw that the friction force is equal to the applied force minus the force times the sum of the masses over 2 times the mass of the wheel plus the mass of the axle. So I'll let you guys look at that, but I think that should be right. Or if that's what you got, then you can just tell me.
Yeah, I think that looks right.
Yeah, I got the same as you, I believe.
Okay. And then wasn't really sure what to put for this, but I said that I was asking if the bicycle wheel was a sphere, would it experience the same rolling friction as the wheel? I said yes, because the translational energy, which is the only thing we use to find the friction force, like this translational component, is independent of moment of inertia. So friction would be the same, even if the shape was different, assuming like the mass and all the other properties remain the same. But I wasn't 100% sure on that. What do you guys think? Does that sound right?
I think that's right. Yeah, that makes
Yeah.
sense.
Yeah, it does.
It's independent of moment of inertia, and nothing's going to
Okay.
change. So it doesn't really matter.
I'll type that up real quick then, so you guys can agree with what I'm writing here.
Wait. I know. I think it should be different. Wait, I think it should be different. Wait, I think it's.
Think it'd be different?
I think no, because it would be different because there's different rolling in nature. I'm pretty sure.
Well, that's what I was thinking too, but the way that you solve like the friction force, you don't worry about the rotational energy, which is dependent on moment of inertia. Because this is just the mass times the translational velocity. So
Uh-huh.
like,
I don't think
as long
anything
as the
changes.
mass was the same, then it would have the same velocity and the friction would be the same.
Yeah, that sounds about right.
Any improvements?
So iffy about this one though, for sure.
Albo tak minimalny, że można powiedzieć, że praktycznie go nie ma. No tak, ma wpływ, ale do pewnego thresholdu, którego ci nie określę, bo nie da się tak
That look good to you guys?
Yeah.
procentami
Yeah.
Okay.
w stanie określić.
And then part two. So part two asks about a string that is wrapped around a uniform disk of mass M with radius big R. And then attached to the disk is 4 low mass rods, each with radius B. And then they have a small mass little m at the end of each of them. So this is like the diagram. And so tells us it rests on a frictionless surface. Tells us that we pull the string with a constant force F, and at the instant when the center of the disk has moved a distance D, an additional length of W of string has unwound off the disk. And so part one, it's asking what is the speed of the center of the apparatus. So in this case, we can just set K trans
Wtedy
equal to
będzie
the
wymagał
work
ode mnie, żeby
done
idealnie.
on the apparatus, which is just equal to F times D. And then just like last time, it's 1/2 mv squared, but we have to take into account the total mass. So that's the mass of the big center part plus the 4 small masses, and then rearrange it to solve for D. And you find that D equals the square root of 2FD over M plus 4 little m. Do you guys get that?
Yep.
Z powodu
Exact same thing.
Okay, cool.
Yeah.
tego, że ewolucja nie działa.
And then this one, it's asking what the angular speed of the apparatus is. So in this case, we're trying to find the angular speed. I thought the best way to do this was to use rotational energy. And so we could set the rotational energy equal to the work done by our
Okej,
hand,
coś
because that would be the
musimy
total
mieć,
work. And then we see that the moment of inertia times the angular speed squared is equal to 2 times force times work, or W. Not work in this case. And so I just broke this down and I solved for I. So 1/2 mr squared is the moment of inertia of the disk. That's like a pretty standard one we've used a lot. And then I had to go back in my notes for this, but point masses that are like suspended on like a massless rod, their moments of inertia are just mr squared. So we know that the radius is B. So I just wrote it as mb squared, and then there's 4 masses, so it's 4 mb squared. And then you just sum the moments of inertia to find the total. And then I substituted that back in to find that the angular speed is equal to root 2 FW over 1/2 mr squared plus 4 mb squared. So that is what I got.
Yeah, that's what I got too.
Yeah.
Okay.
Yeah, I got to fix that. That too.
All right. Well, that is
Let's
it for
go.
recitation.
All right.
So,
Stop recording.